All right, so what would be the difference? This would be f of 2 plus f of 3 plus f of 4. Okay, now you can go onto your calculator and you can do each one of those, right? You're going to plug 1 into this 1 over square root of x. Of course, that would just be 1, 2, and that'd be 1 over square root of 2, and then plus 1 over square root of 3, okay? And then this one, 1 over square root of 2, 1 over square root of 3, and 1 over square root of 4, which of course would just be 1/2. All right, and then out here in front, we just have a 1. Okay, somebody got those decimals? Somebody have those handy real quick? Anybody do the homework? Somebody got a decimal? Speak up. You just went ahead and got the exact, you went ahead and did it already. So what do you got for I minus L3? 0.75. 0.75?
Yeah, and then that's 2 minus 1.863.
Which would be, what was the 0.75?
That was I minus L3.
Gotcha. So what's I minus R3?
2 minus 1.863. I never calculated it.
Okay. So that's a lot smaller, isn't it? So what is that? Well, it should be negative because they all bars around. So what is it? Point what? 215. Do you agree with this one? No. Okay, L3 is like 2.284 something, 1.784, so we get 0.28. What the book has here is this one would be 0.215, I agree, and this one is 0.284. Okay, there we go. So that's 2, take away the L3 and the R3 approximations. Then and then we're supposed to do the error-bound formula. So the formula for both of them, I minus L3 or R3, doesn't matter, is less than or equal to K1, goes right there, 4 minus 1, is that squared, and then the bottom is 2 times n, right? What'd you get for your K1 value right here? What do you got for a K1 value? I can tell you what they use, but I don't like theirs, to be honest with you. See, now, this might be where you got the 0.75. I wonder, because they're saying, does somebody have a K1 value here for me, Maddie? What do you got? Somebody got a K1 value?
I had 0.5 there. Yeah, that's
fine. 0.5?
And that makes.
Okay, that's what the back had. Now, but what do you know what that came out as a decimal? A lot of times we do more decimal places than just one. What did it round? Because remember we talked yesterday about rounding up, bumping it up. Now the back, I don't know if the back had the K value. I don't know if it had that or not. But that's what my answer book uses for K1. But usually, to be honest, their answer book doesn't always pick the best K1 values. Nobody has it? Then we have the decimal unrounded, or it come out exactly. No, this. Yeah, this comes out 0.75. If you put 0.5 in there, I agree. But I'm talking about this value, the max of F prime. Caleb, you got something there? There wasn't exactly. If you go to the max, it's exactly 0.5. So there you go. So if that's the case, so maybe that's what happened. Okay, so good. So if you go to F prime and you graph it and you look for the max between 1 and 4, and it's exactly 0.5, then that's fine. Go ahead and use that, right? We talked about bumping it up, you know what I mean? If it was this long decimal, you would always round up because it's a worst case scenario. But if it's exact, go ahead and use it. That's fine. Okay, so there you get 0.75. Okay, so what is that number now again? What does that represent? What do we call that? What is that? Max error, right? The max error. Okay, that's the most it could be off. What are these numbers here? How much they're actually off, right? So this is how much L3 is off. This is how much R3 is off. This said this is the most they could be off. So are these consistent with the formula? Okay. And notice we said this is worst case scenario. So this number, so this points out a good thing that we didn't cover yesterday. We talked about it, but we didn't see it with actual numbers. Is this points out that this number we find with the formula is actually probably more than the real error is going to be, right? It's the max error. So chances are there isn't that much error, right? Chances are it's not off by 0.75. Chances are it's off by much less than that. And that's what we see here, okay? And that's because we're taking this max. And if you look at the F prime graph, think about this. And maybe there was one of the homework problems. I know there's one we did with. If you got an F prime graph that goes like this, right? Now, and so there's your max, let's say, right? That value. Is that max error going to be reasonably close to the amount of error? Or will it be not close at all to the amount of error? Reasonably close? Why? Because the graph actually has that slope most of the time, right? Most of the time, the graph actually has that slope. So the amount of error is going to be pretty well represented by that number. Conversely, if I've got an F prime graph that goes like that, and I use that as my max slope, is that going to be a very good max error? Not very good at all, because that graph was nowhere near that slope most of the time. It had way less slope. So the graph was really pretty flat until at the end it went up. So there was some error here, but we're going to assume it had that slope the whole time, right? That's what the formula does. The formula assumes it had that slope, that y value right there the whole time. And so that graph was way up here, so we're going to have all this error, when in reality we don't have that error, right? So depending on what your F prime graph looks like, so be prepared to answer some question about that, just understanding how that formula is working, what that K1 value is all about. Again, it's that worst case scenario kind of thing. But this is a good one that shows comparison. Actual error and the formula predicting, not really predicting, but saying, hey, that's the most they'll be off. Okay, and then what was C about? Did that go into midpoints and trapezoids? Compute the actual committed by T3 and M3, so we won't get into that, and then do the formula. And then let's do the last one. So M sub n 0.005. So we want to say, okay, what formula? So, and this is for midpoint now, so we're going to need the K2 value. And then we got 4 minus 1 cubed. And was it midpoint again? I just said it, but I forgot. 24, right? For midpoint, trapezoid to be 12. And we want that to be less than or equal to 0.005, right? So what's your K2 value? It's n squared. Thank you, at the bottom. Okay, so, yes. Okay, so from part C, what was your K2 value? What do you guys got? What do you got for your K2 value, which would be your second derivative max, right? This is measuring the curviness now. Let me see what they've got here. Okay, what do you guys got? Was it exactly that again? 0.75? That's what my book has here. Did it come out exact again? Caleb? You think so? That's weird, okay? And it may have. I can't remember. I don't remember this one. But a lot of times it doesn't, right? When you go to that max, when you look at it, a lot of times it is not exact, right? It is not an exact value. So you've got to bump it up, right? You've got to bump it up. Whatever last decimal place you use, you want to bump that up so you have a worst case scenario. So the back of the book my answer book does say 0.75 for the K2 value. This is a key thing I want you to be able to find. If you're having trouble with that at all, make sure that we can do that. Come see me. If, all you're doing is graphing the second derivative between 1 and 4, or for K1, you're graphing the first derivative between 1 and 4, and you're going to that highest Y value, and then bumping it up a little bit if you have to. We want it to be the max, that value could be. And then we just go under a calculator and solve, and I get a value. They say, I don't know, I assume it comes out of decimal, but they've got 13. Did it come out 12 point something? I'm assuming. But they said 13. So we have to have at least 13 rectangles. Was it exact, guys? Or when you trace to it, the max, it was 0.75. Okay. And then this came out 13. If it came out a decimal 12 point something, of course you would round that to a whole number, because you have to have a whole number of subdivisions. So 13 midpoints will do it for us. Chances are less than that would do it, right? I mean, remember, again, it goes back to this last page. This is the max error. Turns out there's actually less error than that. So that's what would happen most of the time. Well, in this case, 13 rectangles are guaranteed to be within 0.005 of the exact answer, 2 decimal accuracy. But chances are 8 might do it, right? 7 might do it. But we don't know for sure. We wouldn't be guaranteed. That's the beauty of this formula. Since we don't know we do know the exact answer in this problem, but the one we did yesterday, we don't know the exact area. So how do we know how close we are? That's why we need this guarantee. That's why we do this worst case scenario. Okay? So this at least gives us a number that, hey, we can feel comfortable knowing that those first 2 decimal places are going to be accurate if we do 13 midpoint rectangles. Okay? We might get a few extra decimal places for free, but we're going to get 2 for sure. Okay? So that's what we want to be able to do. That's basically it in a nutshell. That problem right there really encapsulates a lot of the important stuff, the really key stuff. Now, obviously, I want you to understand some of the things we talked about here with what that K1, K2 values are really representing, and be able to discuss that as well. But this is the basic stuff we've got to be able to do. You've got to be able to find K1, K2. You've got to be able to plug into the formula. You've got to be able to find this value, or you got to be able to find the n if you're given that value. Okay? For sure. All right. I had down something about 27. Okay? I didn't give you the hats here, so maybe we should look at this. Let's just talk about what's going on with this problem in the various parts of this. They basically talk about splitting this up. Okay? So we're not going to go through all of the nuts and bolts of this, but I do want to graph this, do this derivative. So we've got the derivative, okay, of cosine of 1 over x. Okay, let's copy that. Did I do that right? Was that the function, cosine 1 over x? Okay. Let's copy that. Oh, not there. Control C, if it's highlighted, Control C and then Control V is paste. Control C, Control V. Okay? And you can just type it too, but it's just a nice little shortcut. All right? And so there is that. We only want to, what did they say, from 1 to 11? Okay? And so, set my window. 1 to 11. Let's do a zoom fit. All right, so this is exactly the situation. I couldn't remember if it was this problem or not. This is exactly the situation we were talking about before. So what's your K1 value going to be? At the far left edge, right? Is it 1? Is that what it is? 1, okay. So when you trace there, okay, when you trace over here and you get a 1, okay, let's do that. So we trace, I'm going to shift my graph a little bit. Well, no, it's not 1. It's 0.841. What's that? X value. Oh, okay. Yeah. Where is the K1 value? It would be at 1, right? What is the K1 value? Would be the 0.841. I would round it to 0.842 because I think what's happening is the calculator in the trace mode's only giving me 3 decimal places. So I'm gonna bump that up. So I'm gonna go 0.85. What's that? Oh, I'm sorry. 0.85. I'm gonna call that, or I'm gonna go 0.842. Right? Whatever decimal I stop at, I'm bumping it up one. Okay? You want to go 0.9, that'd be not as good, I don't think, but let's say 0.85. But what do you know about this particular graph from 1 to 11? In relation to the theorem, in relation to K1. Say that again. So most of the time the slope is what? Way, way less than that, right? Almost 0, right? So this graph from 1 to 11 is almost flat. So how much error should it have? Very little, right? But if we use K1 as our as 0.841 or 0.842 or 0.85, right? We use that. That's going to give us not a very useful error bound, right? So what they do is they say, let's split it up, okay? So they say, let's split it up. So if we want the error, and I went ahead and did this, so what they say is, let's go from 1 to 6, and let's have that be within 0.004. Let's take most of the error that we want to have. We only want to have a max error of 0.005. Let's take most of the error and put that at the beginning where the error is going to be, where the graph is a little steeper. So let's put most of the error at the beginning in the first half of the interval and the rest of the error at the end. And let's divide that. So if you do your trapezoid formula, so we're not going to go through it all, but if you use your K1 here of 0.8, let me, just so I can agree with the back of the book here, but if you used a different number, they used 0.8415. Actually, that's good. That's actually a good value. We would have had to trace that. I would have had to get that value. I would have had to went to my calculator side here. Here's my derivative. Now remember how we did that with the vertical bar? I could go over here if I want more decimals, which you wouldn't have had to do here. You could have done 842. I think that would have been fine. 85, I'd have been fine with that too. But if I want to plug, if I can tell on my graph that 1 is where it's going to be, then I can come over here and grab my vertical bar. If you remember, here's how you can plug a number in real quickly. I can go x equals, and that was at 1, right? And so there I can see the actual value and see more digits. So you can see how they did 8415, right? So the back of the book, or at least in my answer book, they used 0.8415. So that gave them 8,400. When they did their formula here and worked this all out, it gave them an N of 8,415 is how many rectangles they needed. Okay? 8,415 left rectangles just to get 2 decimal place accuracy. But if we divide it up this way, the way they suggested, if we divide it up this way and do our formulas, well, we're still going to get the 8415 here, right? And then we'd have 6 minus 1 squared, and we'd have 2 times n, right, like that. And then less than or equal to 0.004. Then when they did that, they come up with, let me make sure I'm looking at the right place, 2,630. So we need n to be, we need 2,630 rectangles to get that degree of accuracy in the first half of the interval. In the back half of the interval, we get a new K1 value because now we're only looking between 6 and 11. And between 6 and 11, they got a K value of 0.005 because that slope is way, way less, right? It's way down here. And so it's pretty flat. And then you go 11 minus 6 squared, and you go 2n less than your 0.001, and it came out to be 63. We only needed 63 left rectangles when you work that out. 63 left rectangles to get within 0.001 in that back half because it's very flat, right? It's very flat, so there's not much error. So it doesn't take very many rectangles. So what would you do now to finish this? Add those two together, right? Add those two together. So if you did two separate calculations, if you did an L 2,630, right, from 1 to 6, and did an L 63 from 6 to 11, you would get an approximation guaranteed to be within 0.005. Because this one would be within 0.004 and this one would be within 0.01. So you would have much less, what's the term they use there? Computational effort? I can't remember if they said that in that problem. There'd be much less computational effort to do that many rectangles. Now for us, there's not much computational effort anyway because we got a program, right? We would just run our program and do 8,000 rectangles or 2,000, whatever, right? But the inside the calculator, there'd be less computational effort to get this done than to do the whole interval. That's what we talked about with that max error thing. Yes.
How did they know where to split it?
They didn't. They just split it in half, right? I mean, they said 1 to 11 is 10, so let's take the first half and do this, and the second half and do this. To be honest, it'd have been better to split it where? Like from 1 to 2, right? I mean, it'd have been better. Yeah, they'd have been better off if we go back to the graph. They'd have been better off going about here, right? And then doing from here to here, and then the rest of it there, because most of the error is in here, right? The vast majority of the error is in here. So yeah, I think they just picked. They just picked, and they said, let's do this. So if we would have done that, if we'd have went from like 1 to 2 or 1 to 3, this number would have been a lot less. And then if we'd have went from 3 to 11, what would you expect would happen to this number? Up a lot? Not very much, right? It wouldn't go up very much. It wouldn't take that many more rectangles, even from 2 to 11 or 3 to 11, because there just isn't that much error in that region, right? So this would go down a lot, I would think, right? If you went from only 1 to 2 or 1 to 3, I think this would go down a lot, and I think this would go up a little, right? And be even better. It'd even take fewer rectangles, okay? So, as far as big picture, how useful, as far as what you need to do as far as doing a bunch of rectangles and stuff, not a big deal, but abstractly understanding what's going on, how this is all tying together, working, it's important. I mean, it's good, good stuff. Okay. All right. So anyway, again, this is another function that does not have an antiderivative. It's one we would not be able to get the exact answer. Okay. All right. So we will save this for tomorrow. So let's hang on here a second. Oh yeah, number 30. I had a note down, something about number 30. What was number 30? Find a value of n that guarantees. Oh, okay. So when they write this, integral 0 to 4, what function is in there?
You don't know, it's a picture.
Oh, it's a picture. Oh, yeah, okay, that's why I want to talk about this picture. So what is this right here? That's just the I, right? That's just the I. They actually put the integral in there. Remember, I is the exact area. So this is just I minus, what is it, L? Ln, and less than or equal to 0, 0, 1. Okay, so we just want to use our formula. 3 zeros. Just, yeah, I got 3 zeros. No problem. All right. So, and then we got the graph down there. It says little f is the antiderivative of that function. So that function would be the f prime, right? That function's the f prime. They, quiz you a little bit there on your terminology, right? Little f's the antiderivative, so that graph would be f prime. All right? And so then they ask us to do this on 30. Well, that's where we get our K1 value, right? Our K1 value comes from f prime. So we look at that graph from 0 to 4. What would you use for your f prime? Nine. Not negative. That's the whole question, to be honest with you. The whole question was, would you recognize that the thing's negative and we want the absolute value of f prime, and so we want 9. Now you are estimating, so if you did 9.5, I'd be fine with that. If you did just 9, I think that'd be okay. 9.2, who knows? You're definitely having to approximate there. Let's just make it simple and just make it 9. Okay? So, but that was the idea. Understanding that's the absolute value of f prime we care about. And so it's the 9, it's that y value there. Then the rest of it would just be 4 minus 0, knowing that this is a left, so you're using this formula. We're using 2n, like that. And that's it. Okay? And go ahead and work that out. I think it comes out to be 720,000.
I had a question. 29A.
Okay, hold that thought. So a ton of rectangles here, right? But they're lefts. And look how big this K1 value is, right? The bigger this value is, the worse it's going to be. I mean, right? Because the bigger this is, the steeper the graph is. Or if it's K2, the more curvy it is, right? So the bigger this number is, the worse it's going to be. The more subdivisions you're going to need. Okay? I mean, that's just, that's what that represents. And so, all right. So what'd you say? Which one?
I only wondered how.
Which one you talking about?
29A.
29A.
How I can see I'm drawing a picture.
Oh, yeah. That's a recognition thing. Now, you're going to get your calculator, so you wouldn't have to do this. But, when it comes to the AP test, you would have to. You would have to recognize this function right here. That is a half circle, centered at the origin, with a radius of 2. And it's the top half. So the area from 0 to 2 would be a quarter circle, so pi r squared would be 4 pi quarter. Yeah. So that's just a recognition of the graph that is a half circle. Yeah. So that's what that one was about. But I'm going to let you use calculators on this whole quiz, so I wouldn't ask a question like that, first of all. But if I did, you could just graph it and see what it was. Okay? Right. Yes?
Do we need to have these formulas memorized?
Nope. The formulas here will be on your quiz page. Okay. What you will have to memorize is what K1 means, what K2 means, and how to find them and so forth. But the actual formulas themselves will be on there. It would look. I'll give you something. I don't think that probably will not be there, and that will not be there. But that will be there, that will be there, that will be there. Okay? All right. Let's take a look at sample 3. So here's what I want you to do. Is I want you to finish on sample 3 the multiple choice section, okay? Because you're going to be looking for something to do this afternoon. So I'll be glad.
I'm gonna be gone.
Oh yeah.
District speech, come on.
I'll be glad to help you fill in that time. Finish the note. Oh, is that what I say?
Finish multiple choice.
Okay, yeah, I misspoke. Finish the no calculator multiple choice section. Finish. Okay. To 28. So we went, now wait, there's one more. And free response number 6. Let's go to that one, the very last problem. Free response number 6. So we're going to finish the no calculator multiple choice. So that's 17 through 28. Oops, I think it went by. This number 6. Here it is. Okay, this is a no calculator one as well. Okay, let's work on this one a little bit right now, and I'll help you as need be. We got about 10 minutes left. So let me just get you started here. They give you this graph of little f, but notice a lot of the questions, B is the exception. Most of the questions are about G, right? So you've got to be careful in your reasoning. It says justify your answer, show your work, all this stuff. You can't be talking about F if the questions are about G, right? Unless you've made some connection. Well, the connection's right here, right? So when you see that right there, it's been a little while, early chapter 5 that we did this. When you see that, what do you think? G is the antiderivative of F. How would I write that? I mean, I could write that out as a sentence, but there's a better way. G is equal to big F. The one that will be the most useful will be that one right there. You could write G is equal to big F, that's okay. But this is the one that really tells the story. So all of these questions, so when it asks for G prime of 4.5, they're really asking for F of 4.5, right? And when they want to know the points of inflection of G, right? You're talking about G double prime, but that would be F prime, right? And so forth, so on. Okay, so that's really the key. They've told you that, which really gives you that, and away you go. So now, hopefully, a lot of that is not too terribly difficult. This is no calculator now. So go ahead and let's work on that for the remaining time. And then, of course, the rest of the time will be those other multiple choice questions, those 12 remaining multiple choice questions. And you're supposed to only get 2 minutes per question. So 12 multiple choice questions, 2 minutes, that's 24 minutes. But it takes a little longer to get it. But a few of them you're going to skip probably because you're going to be like, we haven't done that yet. guys? Yeah. When you, G of 4.5, how do you find that one? I mean, I get these probably. What? It's area, right? Because what's that mean? G of 4.5 means put a 4.5 in for that X right there, right? Which means put one in for that X. Make sense? So it's the area from 0 to 4.5, which is all geometry, right? So we talked about how, geometry is one way to do integrals. You don't get to do it very often because most functions don't make geometric shapes. But a lot of times on the AP test, they do that. They'll give you a graph that makes geometric shapes and get into them. Not always, but some often they do. Okay? And then we've got this formula, remember, for average value. Remember the formula for average value of f? The integral over, right? The integral from -3 to 5 over b minus a, right? That's average value of f. Well, they gave you the f graph, so that's just area, so we get it, right? I mean, so average value. And then you get into some old chart stuff here now, right? You get into some chart stuff here for points of inflection, so you got to review that idea. Points of inflection, remember that? That's second derivative 0, or when g prime is changing, increasing to decreasing, right? G's got to be changing concavity, so we got to be looking at those chart kind of things. So look up the chart again. Same thing with max points. That means global max. Global max. So you got to be talking list of candidates. You got to be talking about those kind of things. Global max, we talked about where the derivative is 0, where the derivative is undefined, where endpoints, right? Remember list of candidates? Not local max. This is talking about global max. So that's good review of those ideas.
Okay, so I did go from 0 and I got 13.
I got that. But you got 13.5.
I didn't start at 0. Because at first I did the whole thing.
Oh yeah. Well, it says from 0 to X. So.
Yeah, and then X is the whole thing. That's where I got 13.
Alright, solid. I don't know. We're watching a video, Disney.
Should I take on it?
No, because we're watching that.
No, I got early and I put down all the notes, but leave them there.